A very warm welcome to all guests, delegates, resource persons, and all participants from different parts of India and abroad. I, Dr. Jayasree Das, convener of this webinar, feel privileged to welcome you all on behalf of Department of Mathematics, Chittaranjan College. In light of present pandemic caused by COVID-19, we all human beings are working towards a major paradigm shift in teaching, learning, and evaluation. Today, Department of Mathematics of Chittaranjan College, in collaboration with IQAC of Chittaranjan College, are going to organize one-day national webinar on Soliton, a qualitative approach for UG and PG students, research scholars, and faculty of colleges and universities. In mathematics and physics, a soliton is a self-reinforcing wave packet that maintains its shape while it propagates at a constant velocity. Before going to our main topic, I invite our IQAC coordinator, Dr. Paromita Das, for her welcome address.
I think I am audible. Am I audible?
Yes, you are audible.
Thank you, Dr. Jayasree Das. It's my great pleasure to accept the proposal of the Mathematics Department and our organizing committee to arrange a webinar on solution, a qualitative approach. So, on behalf of IQAC committee, I welcome our respected resource person, Dr. Anup Bandhyopadhyay, Professor of Department of Mathematics, for honoring our request. I welcome all the participants, respected professors, scholars, and students. Thank you all for joining us. Hope you will have an enlightening experience today. I wish the organizing committee for the grand success of the program. Thank you very much. Over to Jayasree.
Thank you, madam, for your inspiring and motivating speech. Now I request Professor Soumi Mondol to introduce our speaker to the participants. Over to Professor Soumi Mondol. সৌমি আনমিউট করো।
Sorry. Thank you, Dr. Jayasree Das. Very good afternoon to everyone. Today, our eminent resource person is Professor attached with the Department of Mathematics, Chittaranjan College under University of Kolkata. Professor Bandhyopadhyay is associated to several selection committees and rendered his responsibility as the subject expert in those. He is also associated as reviewer of some reputed international and national journals as well. Professor Bandhyopadhyay has a wide range of exposure in the field of plasma physics, non-linear phenomenon of wave, dusty plasma physics, non-linear wave process in plasma dynamics, hidden Hamiltonian plasma process in plasma dynamics, linear and higher order stability, and related topics. He is also associated as a coordinator of Center of Plasma Studies, Jadavpur University, which was established with the formal approval of university in the year 1993-94. The Government of India has identified plasma studies as one of the important areas of science and technology, requiring major research and further academic explorations. Keeping in tune with the worldwide advancement in plasma physics that has become a viable source of industrial application in several areas of technologies. He is also a life member of Advanced Center of Nonlinear and Complex Phenomena, being in the profession of teaching for more than 40 years as an enthusiastic teacher, educator, and researcher. Professor Bandhyopadhyay has done all his academic and administrative duties skillfully. He has organized various conferences, seminars at various levels. There are some PhD students who have got their degrees under his able supervision and are still doing so. He has presented a number of papers in several national and international seminars and has published more than 30 papers on many research articles in peer-reviewed journals of national and international level. Over to you, sir. Professor Dr. Onu Bandhopadhyay. Sir, am I audible? Over to Professor Bandhopadhyay.
Yes. Okay. So
Sir, very
thank
good
you.
afternoon.
So today topic is Soliton, a qualitative approach or a qualitative study. Have you seen this? Hello? Hello?
Ha, sir. No, sir.
Yes,
Your
definitely, sir.
presentation is not visible.
You see?
Yeah. It's starting. It's starting. Yes.
Okay.
Yes, sir. Yes.
Uh, so what is Soliton? Soliton, first of all, it is a nonlinear wave whose shape and size remains unchanged during its motion. And because of the particle-like behavior of soliton, it can transfer full energy from one place to another. So, today's talk, outline of the talk is just of this. We considered the definition of solitary structure from the very basic equation. This is the energy conservation equation known as energy integral. And then we considered the dynamical system consisting of two coupled equations. And number three is we make a one-to-one correspondence between solitary structures and separatrix of the phase portraits of the dynamical system. And the fourth one is the transition process of different solitary structures, that is from soliton to double layer to supersoliton to soliton again. Now, first of all, what is soliton? To define a soliton, first of all, we consider a very basic fundamental equation. And you know this type of equation, this is the energy conservation equation. And the first term, this is the equation of motion of a particle of unit mass. whose position is phi at times I, with velocity defined as I. So once again, you see, this is the equation, conservation of energy of a particle, uh, whose position is phi at times I with velocity defined as I. We consider the mass of the particle is unit mass. So the first term, this can be regarded as the kinetic energy of the unit particle at position phi and times I, and V phi is the potential energy of the same particle. And as kinetic energy is a non-negative quantity, V phi less equal to 0 for the entire motion. That is, 0 is the maximum value of V phi. So here you can write the equation of conservation of energy is of the form that is the kinetic energy plus potential energy is equal to a constant, and you can shift this constant into the left hand side to make it that potential energy plus kinetic energy plus potential energy is equal to 0. This is actually a you can translate the reference from frame, nothing else. So you see that you can always write the conservation of energy in this form: half of d phi dji whole square plus v phi is equal to 0. Here we take the mass of the particle is unity. So and this equation is known as energy integral. So we call it energy integral, and this is the energy integral. If you differentiate this equation with respect to phi, then you have this equation, that is d square phi dj square is equal to minus v dash phi. And you see, as the mass of the particle is 1, so 1 into d square phi dj square is equal to minus v dash phi. So the velocity of the particle can be taken as root over minus 2v phi, and the particle is under the action of the force field minus v dash phi. Suppose you have considered, so this is the motion of the particle. Motion of the particle is along the phi axis, and you take a position, that is, you take a point O which is fixed on the phi axis, and therefore the phi axis, this has got two directions. One is along n cap and the other is along minus n cap. We take a position P on the phi axis, and this is the position of the particle at times I. Therefore, what is the position vector of the particle? Position vector of the particle with respect to the point O, we have OP vector, and which is equal to phi n cap. This can also be written as minus phi into minus n cap if the particle is on the left side. And therefore, the force acting on the particle at P, this is the mass into the second derivative of the position vector with respect to time. And this is 1 into d squared dj square into OP vector, because here xi is equal to the time coordinate, and therefore d squared dt square, that is d squared dj square of OP vector, which is equal to d squared dj square into OP vector, position vector of the particle. This is equal to phi n cap, and this is equal to d square phi dj square n cap. And we can write, you see, d square phi dj square, this is the force field, and you see the force field here minus v dash phi. So this is equal to minus v dash phi, and this can be written as v dash phi into minus n cap. So the force acting on the particle at P is minus v dash phi n cap or v dash phi minus n cap. Now, next, suppose the particle is on the right side of phi axis. So that is phi is greater than 0. If this be the case, then you see the force at P is V dash phi into minus n cap. V dash phi into minus n cap, and therefore you see if V dash phi is greater than 0, then the particle is along then the force is along the direction of O. You see again, if V dash phi greater than 0, then what is the direction of the force? If V dash phi greater than 0, then the force is along O. That is, the force is directed along O. That is, the force is directed along the point O. That is, you see, the force acting on the particle at P is directed towards the point phi is equal to 0 if and only if V dash phi greater than 0 for phi greater than 0. Once again, you see the force component. You see the force, if V dash phi greater than 0, then the force acting on the particle is directed towards the point O, is directed towards phi is equal to 0, and therefore we have the force acting on the particle at P is directed towards phi is equal to 0 if and only if V dash phi greater than 0 for phi greater than 0. Suppose the force particle is on the left side of phi axis, that is phi is less than 0, and therefore the force acting on the particle is again minus V dash phi n cap. Now, if this quantity is positive, that is minus V dash phi is positive, then the force acting on the particle at P directed towards the point O. You see again, so if V dash phi, this is positive, if V dash phi minus V dash phi is positive, then the force acting on the particle at P is directed towards n cap, that is towards this. And therefore, the force acting on the particle at P is directed towards origin if and only if minus V dash phi greater than 0 for phi less than 0, or V dash phi less than 0 for phi less than 0. And therefore, the velocity of the particle is governed by minus 2 root over minus 2 v phi. The particle is under the action of the force minus v dash phi, and the force is attracting one if and only if v dash phi greater than 0 for phi greater than 0, and you see v dash phi less than 0 for phi less than 0. So if you see, if the velocity of the particle is 0 and the force acting on the particle is 0, then the particle is in equilibrium. Therefore, you see, for equilibrium at phi is equal to 0, that is the equilibrium position of the particle at phi is equal to 0, we must have the velocity of the particle at phi is equal to 0 is 0, that is v0 is equal to 0, and the force acting on the particle at phi is equal to 0 is 0, and therefore v dash 0 is equal to 0. Therefore, for equilibrium at phi is equal to 0, we must have v0 is equal to v dash 0 is equal to 0, and therefore the particle is in equilibrium at phi is equal to 0 if and only if v0 is equal to v dash 0 is equal to 0. So next we take this one, that is we take v0 is equal to v dash 0 is equal to 0. That is the particle is in equilibrium at the point phi is equal to 0. In this case, you see we have three cases. Case 1, you see v double dash 0 greater than 0. That is the uh, that is that is potential energy. This is minimum at the point phi is equal to 0. In other words, v phi, this is concave or locally concave at the point phi is equal to 0. Next is v double dash 0 is less than 0. This implies potential energy at phi is equal to 0 is maximum, or in other words, the v pi, the curve v pi with respect to phi is locally convex with respect to the point phi is equal to 0. And number 3 is v double dash 0 is equal to 0. In this case, we have phi is equal to 0. This is the point of inflection of the curve v phi at the point phi is equal to 0. So we have these three cases. Now we consider these three cases and discuss the birth of the soliton. So first one, suppose v0 is equal to v dash 0 is equal to 0. This gives that is the particle is in equilibrium at phi is equal to 0 and v double dash 0 greater than 0. This gives the potential energy is minimum at the point phi is equal to 0. So potential energy is minimum, that is we have this figure. So potential energy is minimum, this gives from the energy test of stability, potential energy is minimum, this gives actually the particle is in stable equilibrium. That is, if a particle be slightly displaced from its position of equilibrium, then uh, it moves towards its position of equilibrium. And in this case, you see, except the point phi is equal to 0, v phi is strictly positive, which contradicts the fact that 0 is the maximum value of v phi. And in this case, it is impossible to make any oscillation of the particle for which v phi is less equal to 0. So you see, we for this case, it is not possible to get an oscillation of the particle for which v phi is less than 0. Next case, that is, we consider this one, v0 is equal to v dash 0 is equal to 0. This condition gives the particle is in equilibrium at phi is equal to 0, and v double dash 0, this is less than 0, and this gives actually the potential energy, this is maximum at phi is equal to 0, and from the energy test of stability we get that phi is equal to 0 is a position of unstable equilibrium. And this implies from the if a particle be slightly displaced from its position of unstable equilibrium, then you see that the particle moves away from its position of equilibrium, and it continues its motion until its velocity is equal to 0. That is, until phi takes a value phi m, where v phi m is equal to 0. This gives the velocity of the particle at phi is equal to phi m is 0. So if a particle be slightly displaced from its position of unstable equilibrium, then it moves away from its position of equilibrium and it continues its motion until its velocity is equal to zero. And suppose there exists a value phi m where v phi m is equal to zero. That is, the velocity of the particle at phi is equal to phi m is zero. So we have these conditions, that is v0 is equal to v dash 0 is equal to 0, that is the particle is in equilibrium position at phi is equal to 0, and the position of equilibrium is unstable position of equilibrium, and there exists a phi m for which v phi m is equal to 0 and phi m not equal to 0. So we have, this is the schematic diagram. This is, you see, this is phi m where v phi m is equal to 0. And if you draw the tangent to the curve at phi is equal to phi m, then it makes an angle theta with positive direction of phi axis. So you have, you see, tan theta is equal to v dash phi m, and as theta lies within 0 and phi by 2, tan theta greater than 0, which gives v dash phi m greater than 0. Therefore, you see, for phi m greater than 0, you have v dash phi m greater than 0. Therefore, at this point, that is at phi is equal to phi m, the force acting on the particle is directed towards the point phi is equal to 0. So you have a particle at phi is equal to 0, and if you slightly displaced it towards the positive direction of phi axis, then it moves away from its position of equilibrium and it continues its motion until phi takes the value phi m, where v phi m is equal to 0, but the force is acting towards the point phi is equal to 0. So you have an oscillation of the particle in 0 and phi m. So now let's suppose v0 is equal to v dash 0 is equal to 0 and v double dash 0 less than 0, v phi m is equal to 0, but here we take phi m is less than 0. So what is the figure? Figure is just like this is the schematic diagram of v phi within 0 and phi m. So here you see this is phi m, and you have v phi m is equal to 0, and you see this is the tangent to the curve at phi is equal to phi m, and this tangent to the curve at phi is equal to phi n makes an angle theta with the positive direction of phi axis, and you see v dash phi m which is equal to tan theta, and as theta lies between pi by 2 and pi, this is less than 0. So you see that we have phi m less, for phi m less than 0, v phi m is equal to 0 and v dash phi m is less than 0. Therefore, the force acting on the particle at phi is equal to phi m is directed towards the point phi is equal to 0. Therefore, if you have a particle at phi is equal to 0, and if the particle be slightly displaced towards the negative direction of phi axis, then it moves away from its position of equilibrium phi is equal to 0, and it continues its motion until phi takes the value phi m, where v phi m is equal to 0 and v dash phi m less than 0, and this gives the particle, that is, here you have the particle, and the force acting on this point, force acting at phi is equal to phi m is directed towards the point phi is equal to 0, and therefore you have an oscillation of the particle within phi m and 0. So For the oscillation of the particle, we have V0 is equal to V dash 0 is equal to 0 and V double dash 0 less than 0, where phi, that is phi is equal to 0 here. This is the unstable position of equilibrium. And you see V phi m is equal to 0 and V dash phi m less than 0 for phi m less than 0, or V phi m is equal to 0 and V dash phi m greater than 0 for phi m greater than 0. And this condition required for the oscillation of the particle within 0 and phi m or phi m 0, as the case may be. And this is the third condition, that is V phi is less than 0 for minimum of phi m and maximum of phi m. And this condition is necessary to define the energy integral, because you see the energy integral, this is half of that is V phi is negative within the interval, that is 0 phi m and or phi m 0. So these are the condition for the oscillation of the particle. Now, if you place such oscillation in a wave frame moving with the velocity m, capital M, then the oscillation obviously propagates with the velocity capital M, and consequently one can get a wave, and this wave is known as soliton. So first of all, what is wave? For wave, you must have an oscillation, and if the oscillation propagates with some velocity, then you have a wave. So here we have a oscillation, and this oscillation, and if this oscillation propagates with the velocity, we get a wave, and this wave is known as soliton. And why it is soliton? We are considering different types of waves, say sine waves, cos waves. These are coming from the linear equations. But here, we first of all, perhaps this is the first nonlinear equation in the real world. That is the wave equation, that is the conservation of energy, that is the kinetic energy plus potential energy. This is equal to constant. This is the first nonlinear equation in the real world, and therefore this wave is the oscillation is nonlinear oscillation, and if this nonlinear oscillation propagates, then we have a soliton, and this is known as soliton. And for phi m greater than 0, this soliton is known as positive potential solitary wave, and for phi m less than 0, this soliton is known as negative potential solitary wave. Now for soliton, oscillation takes place in a wave frame moving with the velocity capital M. Therefore, in the wave frame, the energy integral assumes the following form: half of d phi dj here whole square plus Vm phi is equal to 0. That is V phi, this is actually not the function of phi only. This is function of m and phi, where m is the velocity of the wave frame. So, condition for the existence of solitons, simple. V of m0 is equal to V dash m0 is equal to 0 and V double dash m0 less than 0. And condition 2, Vm phi m and V dash m phi Vm phi m is equal to 0 and V dash m phi m greater than 0 for phi m greater than 0. And here you see this phi m, that is phi m depends on m, capital M. And third one, Vm phi, this is less than 0 for the interval 0 phi m or phi m 0. This is the condition for solitons. So now if there exists an m such that this is equal to 0, that is Vm phi m is equal to V dash m phi m is equal to 0. That is, you see, that is the velocity as well as the force at the point phi is equal to phi m vanish, simultaneously vanish. force and the velocity at the point phi is equal to phi m simultaneously equal to 0, then what happens? Along with the above two conditions, that is 1 and 3. Then instead of, you see, the velocity as well as the force on the particle at phi is equal to phi m, both are equal to 0. And the particle will not be reflected back again at the point phi is equal to 0. So in this case, instead of soliton, one can get a shock type shock type solution of the energy integral, and this energy integral, this solution is known as positive potential double layer (PPDL) for phi greater than phi m greater than 0, or negative potential double layer for phi m less than 0. So you see, this is the positive potential soliton. That is, we have, you see, this is the, and if theta approaches to 0, then we have this curve. If theta approaches to 0, then we have this curve. And you see, this is the double layer. From one, you see, we have this one, that is the positive potential solitary wave, positive potential soliton. If theta approaches to 0, then we have double layer, positive potential double layer. So existence of positive potential double layer implies the existence of at least one sequence of positive potential solitary wave converging to that of positive potential double layer. So existence of positive potential double layer implies the existence of at least one sequence of positive potential soliton converging to that double layer. Or a double layer solution, this is the ultimate solution of the positive potential soliton. That is, any sequence of positive potential soliton ends with a positive potential double layer if exist. And therefore, this is the profile of V phi versus phi for PPDL through PPSW to PPDL. And profile of this is simple. You see here we have a negative potential solitary wave, that is phi m is less than 0, and if theta approaches to pi, then we have this v dash phi m is equal to tan theta is equal to tan pi is equal to 0. V phi m is equal to 0, v dash phi m is equal to 0, and we get a negative potential double layer. Therefore, existence of negative potential double layer implies the existence of at least one sequence of negative potential solitary wave converging to that double layer solution. Okay. Next, we consider the case when v double dash m phi m is equal to 0. We have considered the case when v double dash phi m greater than 0, v double dash phi m less than 0. Here we consider the case v double dash phi m is equal to 0. This is the main case. You see, v0 is equal to v dash 0 is equal to 0. And for this case, for the first one, you see v double dash 0m less than 0. Actually, this inequality gives m greater than, there is, mc is a critical value, and there exists a critical value mc such that m is greater than mc. And for m greater than mc, you have unstable equilibrium, and you have the positive or negative potential solitary wave. For m less than mc, there is a stable equilibrium, and it is not possible to get any soliton. And v double dash 0 mc is equal to this actually gives V 0 M is equal to 0. This actually gives M is equal to MC. And our aim is to discuss this case V double dash 0 MC is equal to 0. What happens? So V double dash 0 MC is equal to 0. Suppose V double dash 0 V double dash MC 0 is equal to 0, along with V triple dash MC 0 is equal to 0. In this case, general prescription is to compute V4 MC 0. If V4 MC 0 is less than 0, then potential energy is maximum, and therefore we have unstable equilibrium, and therefore solitary structure may exist. If V4 MC0 greater than 0, then we get stable equilibrium, then it is impossible to get any solitary structures. So if V triple dash MC0 is equal to 0, along with V double dash MC0 is equal to 0, this case is very simple. But if you get V double dash MC0 is equal to 0, along with V triple dash MC0 is not equal to 0, then what happens? Then we have considered this theorem. This theorem actually, to consider this case, we have actually proved 10 important theorems to confirm the soliton, to confirm the existence of soliton at M is equal to MC. Theorem 1, first theorem, very important one. This is V triple dash MC phi bears the same sign with, that is, there exists a neighborhood of phi, neighborhood of phi at phi is equal to 0, such that V double dash MC0 and V triple dash MC0 and V triple dash MC phi greater than 0. This actually implies, you see, V triple dash MC phi, this bears the same sign with V triple dash MC0. This is very simple. And next, we have this formula, that is V triple dash MC0 into V double dash MC phi greater than 0 within a positive neighborhood of phi, about phi is equal to 0. Within a positive deleted neighborhood of phi is equal to 0. Right? So we have this theorem, and you see this one, V double dash MC phi. This actually states that V double dash MC phi bears the same sign with V triple dash MC0 within a positive deleted neighborhood of phi is equal to 0. And next one is this, you see, V triple dash MC0 into V double dash MC phi less than 0 within a negative deleted neighborhood of phi is equal to 0. So you see this one, V double dash MC phi, this bears the opposite sign with V triple dash MC0 within a negative deleted neighborhood of phi is equal to 0. Or left or right, you can call, this is the left deleted neighborhood and this is the right limited deleted neighborhood. 0 to phi epsilon, you can call it as a deleted right neighborhood of phi is equal to 0 and deleted left neighborhood of phi is equal to 0. So we have next theorem. Suppose you consider this one, that is, suppose V triple dash MC0 is less than 0. Then what happens? Then from the first case, you see V triple dash MC0 into V double dash MC phi, This is greater than 0 for 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 right neighborhood of for a right deleted neighborhood of phi is equal to 0. So this gives actually V doubled as MC phi. This bears the same sign of V tripled as MC0 within the right neighborhood. So V doubled as, you see V tripled as, if V tripled as MC0 is less than 0, then we have V doubled as MC phi. This is less than 0 for 0 less than phi less than epsilon. That is, we have V double S MC phi. This is less than 0 within a right deleted neighborhood of phi is equal to 0. And this implies actually that V phi, this is convex within a right deleted neighborhood of phi is equal to 0. Therefore, if a particle be slightly displaced along the positive direction of phi axis, then it immediately falls into this region, 0 to phi epsilon. And due to convexity of this region, it moves away from its position of equilibrium. And it continues its motion until its velocity is equal to 0. Therefore, for this case, one can get a positive potential solitary wave. On the other hand, if this holds, V doubled as MC phi, you see, within a left neighborhood of phi is equal to 0, within a left neighborhood of phi is equal to 0, V doubled as MC phi bears the opposite sign of V tripled as MC0. And therefore, V doubled as MC phi, this is greater than 0 for left neighborhood of phi is equal to 0. And therefore, in this region, the function V phi is concave. And therefore, due to concavity of this region, if a particle be slightly displaced in the negative direction of phi axis, then it moves towards the point phi is equal to 0. And therefore, there is no oscillation of the particle. So, for this region, it is impossible to get any solitary structures. So, for this region, you may get a solitary structure, and for this region, it is not possible to get any solitary structure. And consequently, we have this theorem. If V tripled as MC0 less than 0, there may exist a solitary structure at M is equal to MC in the positive potential site, that is phi is greater than 0. Phi is known as, sometimes phi is known as potential. And there does not exist any solitary structure at M is equal to MC in the negative potential site. Similarly, for V tripled as MC0 greater than 0, there may exist a solitary structure at M is equal to MC in the negative potential site, but there does not exist any solitary structure at M is equal to MC in the positive potential site. And theorem 5, this is actually the combination of these two theorems. It is impossible to get coexistence of both positive and negative solitary structure at M is equal to MC. Because you see, at M is equal to MC, either V tripled as MC0 is greater than 0 or V tripled as MC0 is less than 0. Because V tripled as MC0, our assumption is V tripled as MC0 is not equal to 0. Either it is greater than 0 or it is less than 0. If it is greater than 0, then you have a positive potential solitary wave. Or if you have, if V tripled as MC0 is greater than 0, then you have a negative potential solitary wave. So, it is not possible to get coexistence of both positive and negative potential solitary structures. Next theorem, you see V tripled as MC0 is less than 0, and we have added an extra condition, that is del V del M is less than 0 for all m greater than 0. This condition actually automatic. This condition is actually automatic condition. This holds good for any system. However, we take this b triple dash mc0 less than 0, and we take del v del m is less than 0 for all m greater than 0. And the system supports PPSW, positive potential solitary wave, for the right neighborhood of MC. Because MC less than M less than M0. That is, there exists a right neighborhood of MC where the system supports PPSWs. Then either there exists a PPSW or there exists a PPDL at M is equal to MC. Moreover, the PPDL solution at M is equal to MC is possible only when the curve M is equal to M PPDL tends to intersect the curve M is equal to MC. So you have a curve M is equal to MC in the compositional parameter space, and you have a curve M is equal to M PPDL in a compositional parameter space. And if the curve M is equal to M PPDL tends to intersect the curve M is equal to MC at some point in the compositional parameter space, then instead of PPSW, we have a PPDL. And next theorem. Next theorem, you see B triple dash MC0 greater than 0, and the system supports this. System supports NPSWs for all M within a right neighborhood of MC. System supports NPSWs within a right neighborhood of MC. Then we have either NPSW or NPDL at M is equal to MC. And NPDL solution at M is equal to MC. At M is equal to MC, this actually means V double dash M is equal to 0. If you solve this equation, V double dash M0 is equal to 0, then you have M is equal to MC. M is equal to MC, this is nothing but the solution of the equation V double dash M is equal to 0. Okay, so moreover, if NPDL solution at M is equal to MC, this is possible only when the curve M is equal to NPDL tends to intersect the curve M is equal to MC. And Theorem 8, if B triple dash MC0 less than 0 and the system supports NPSWs within a right neighborhood of MC, then there does not exist PPSW as well as PPDL at M is equal to MC. And V double dash MC greater than 0, along with the system supports PPSW within a right neighborhood of MC, then there does not exist NPSWs as well as NPDL as M is equal to MC. And if B triple dash MC0 not equal to 0, along the system supports coexistence of both PPSWs and NPSWs, then either PPSW or PPDL at M is equal to MC, or NPSW or NPDL at M is equal to MC. So these are the 10 important theorems. So now we consider a plasma system. You can consider any system, but here we take a plasma system. You know what is a plasma? Plasma is a fourth state of matter, that is the charged particles here, the charged particles, and that is electrons, ions, positrons, etc. These are the charged particles, and we take here adiabatic warm ions, isothermally or non-thermally distributed. These are the distribution means that you know the probability distribution, the same thing. we have some isothermally distributed. This means actually the electrons follow the Maxwell distribution or Gaussian distribution. And similarly, isothermally or non-thermally distributed positrons and negatively charged static dust particles. And the equation of continuity, these are the four equations actually. And equation of continuity, this is actually the conservation of mass actually. This is conservation of mass. Equation of motion, this is the conservation of momentum. And equation of pressure, that is equal to the conservation of energy. And Poisson equation, this Poisson equation is coming from the Maxwell equations. That is, here we consider actually the particles, that is, there is magnetic field is that is del v vector, that is the magnetic field is constant, that is uniform. And static, uniform, this means actually space independent. Static, this actually means time independent magnetic field. And therefore from Maxwell equation, it follows that del cross E is equal to 0, because del cross E is equal to del V vector by del T. This is the Maxwell equation. And from Maxwell equation, it follows that E vector is equal to minus del vector phi. And therefore we can write from Gaussian equation and from Maxwell equation, we can write del square phi is equal to this. And therefore you see, these are the state equations. And lifting all the basic equation in the wave frame, which is moving with a constant velocity normalized by the linear velocity of DIA waves. In the present plasma system, we derive the following nonlinear ordinary differential equation known as this energy integral. V phi, this is actually Vm phi. Actually, V depends on the parameters of the system. This mu, p, beta e, beta p, etc., sigma I, sigma p, these are the parameters of the system. And this can be easily obtained by using the transformation, very well-known transformation, xi is equal to x minus mt for the case of one dimension. And for the case of 3 dimension, it can be taken as x lx y ly plus y ly plus z lz minus mt, where lx or ly lz, these are the direction of the these are the unit vector, that is lx ly lz. This is the direction cosine of the straight line, that is directed line along which the wave is propagating. And we have, for this case, we have this one V0 is equal to, and this one MC. This gives actually V0 is equal to V dash 0 is equal to 0 and V double dash 0 less equal to 0. This implies M greater than MC. That is, in general, solitary structures start to exist for supersonic wave. That is, M is greater than MC. MC is the lower bound of the Mach number. For the this M is sometimes known as Mach number. Sometimes it is not. M can be taken as the actual velocity of the wave frame. But if you make it dimensionless, then M can be taken as Mach number. And Mach number, this Mach number is greater than MC. That is, MC is the lower bound of the Mach number for the existence of solitary structure. That is, the solitary structures start to exist for M greater than MC. This MPPDL, that is, we consider a curve here, M is equal to M NPDL, and we have along this curve, M is equal to M NPDL, one can get negative potential double layer solution. And for this curve, that is M is equal to M PPDL, one can give a positive potential double layer solution. And M max, this is the upper bound of the Mach number for the existence of PPSW or NPSWs. And case if M max and MPPDL both exist, then the upper bound for the existence of positive potential solitary structures is obviously given by max of this. and otherwise MC less than M less equal to M max. And for case 1, we have an interesting case if MPPDL is less than M max. So you see the case MPPDL is less than M max. We have two types of solitons. First type of soliton, this is bounded by MC less than M less than MPPDL. That is, you see for the first type of soliton, you have a sequence of positive potential solitary structures converging to the double layer solution. And for the second type of solution, this is bounded by MPPDL less than M less than M max. So you see, for this case, we have a soliton after the formation of double layer. So soliton after the formation of DL means double layer, and we have, you see, M is equal to MPPDL minus epsilon. You see this is the curve phi versus V5, and for the curve A, you have, this is the MPPDL minus epsilon. That is, M is slightly less than MPPDL, and for this case you have a soliton. And for M is equal to MPPDL, you have positive potential double layer, and for this case you see this is the curve for M, for which M is slightly greater than MPPDL, and therefore you see this is the fourth one. That is, this gives you actually the phi versus curve of phi, that is the phi of curve of phi versus xi. This gives the, so you see this is the trajectory. Actually you see that is V5, this is this is the phi versus, and you see from this curve, that is curve D, there is a jump type of discontinuity of the amplitude of the solitons, because you see epsilon, you can take epsilon as small as you please, and for this case you see there is a jump type of discontinuity of the solitons just before and just after the formation of double layer. So there is a, so we have a nice structure, but it is not possible to define this type of structure that is just before and just after the formation of double layer. So to distinguish between these two structures, that is the structure just before and just after the formation of double layer, it is PPSW after the formation. So here also you see another example. You see this is, we have the first one, first curve is M is equal to M NPDL minus epsilon. This is dash curve. Dash curve, this gives you the M is equal to M NPDL, that is slightly less than M NPDL. M is equal to dash curve, this is M is equal to M NPDL minus epsilon, and this is slightly less than M NPDL. And solid one, this is M is equal to NPDL, and dash dot curve, this actually gives you slightly greater than M NPDL. Epsilon is a very, very small quantity. You can take it. So you see, there is a jump type of discontinuity here also, and there is a NPSW after the formation of NPDL. So you see from M NPDL to M NPDL plus epsilon. The first one, that is in the upper panel, you see we have M is equal to M NPDL. Whereas for the lower panel, we have M NPDL plus epsilon. So soliton after the formation of double layer also. So actually, what is the distinction between these two? To make a clear distinction between these two, it is also super soliton structure for this region, super soliton. Now, what is super soliton? It is another important topics, and to discuss this problem here also super soliton structure. Or to discuss this problem, we go through the dynamical system. So if you differentiate this with respect to this is the energy integral, and if you differentiate this with respect to phi, you have this equation, and you see this equation can be placed as this two coupled equation, and this two coupled equation, and what is the relation between the soliton and the phase portrait of the dynamical system? This is the first interesting question. Or is there any relation between these two? So our task is to make a correspondence between soliton and the phase portrait of the dynamical system. Now, what is the correspondence? The correspondence is any solitary structure is the separatrix of the phase portrait of the dynamical system that appears to start and end at the origin, enclosing a non-saddle fixed point. The origin is the saddle point of the dynamical system. So you see the soliton is nothing but the solitary structure. Any solitary structure is nothing but the separatrix of the phase portrait of the dynamical system that appears to start and end at the origin, enclosing non-saddle, etc., etc. But the final important point is the origin is a saddle point of the dynamical system. The origin is the saddle point of the dynamical system. So you see solitary structure, any solitary structure, the soliton or double layer or super soliton or soliton after the formation of double layer, etc., etc. Any solitary structure is the separatrix of the phase portrait of the dynamical system. Now, what is the difference between these separatrix? You see, first of all, this is the separatrix. The blue one, you see, first in the first one, that is in the upper panel, we have drawn phi versus v phi, and in the same axis, we have drawn the phase portrait. You see, this is the separatrix. The blue line in the lower panel is the separatrix. You know what is separatrix? Separatrix, just you can think that is a separatrix is a curve which can separate actually two family of curves. You see, within the separatrix we have curve. You see, that is the red curve. We have curve marked by red one. Okay. And outside the separatrix, we have curve marked by dashed line. Okay, so you see the red curve. This actually corresponds. This are closed curve, and this star is actually solid star. This is the stable fixed point. This is actually the stable fixed point. You know the stable points, that is v double dash 0 is equal to 0, v double dash, etc., etc., and v dash. You see the stable point. You know what is stable point, and this star is the stable point, and this solid circle is the unstable fixed point or saddle point. You see, this is the saddle point. So you see, every maximum of v phi corresponds a saddle point, and every minimum point of v phi corresponds a stable fixed point. this one, actually you see, this is the saddle point. This is actually, see, that is the car separatix is not passing through the saddle point. It is not possible for a separatix to pass through the saddle. So the separatix can go as close to any separatix is close to this point, to the saddle, but it is not possible for a separatix to go to pass through the saddle. Okay, so this is the separatix. You see the separatix, and you see this is also a separatix. This is the blue car. This is the solid circle. You see every solid circle that is corresponds to the maximum point, and star corresponds to the minimum point. You see this, and red car, this is actually the this corresponds to the periodic wave. You can see that this is the periodic stable point. You know, the periodic wave, just like motion of a pendulum. This is just like this, and motion of a pendulum. This can be this can be originated from the stable point at theta is equal to 0. You know this, and here also this motion of a pendulum. This is x is equal to a cos theta, y is equal to a sin theta, and therefore you have, this is the periodic type of wave, x square plus y square is equal. That is the closed curve, closed circle. Here also the curve is closed, but not the circle. Sometimes known as nonlinear periodic waves. Similarly, you have the super nonlinear periodic waves. This one, you see, this is nice. You see, this is, you have the separatix at the point, you see, it appears through the point, through the saddle 0. That is the blue one, sorry, separatix blue one, which is the separatix, that is the blue car. This starts to appears at the point appears at the point phi is equal to 0. You see, yes, and it contains another separatix. This is green one, because you see the point for 1.05, for phi is equal to 1.05. You see, for phi is equal to 1.05, you have v phi is minimum, and as v phi is minimum, corresponding saddle given by small solid circle is a saddle, and therefore you have a car green one, which is passing through the saddle, and they are passing through the saddle at the point 1.05. Passing through the saddle, this means actually not passing through the saddle. This is this curve is close and close to the point, to the saddle, and this so you have a you see separatix, that is green one, and you have another separatix, that is blue one. So this separatix, that is the blue one, contains another separatix, green one. So this is the difference between a Supersonic structure and Soliton structure. Once again, you see any Supersoliton structure, any separatrix for Supersoliton structure contains another separatrix. And separatrix, that means which can separate two family of cards. You see, for the green one, you have uh, green one. You see, green one. This separates two family of cards. One is red one, and another are also closed card outside the green one, not given in the diagram. You see, and the Neil and the blue one, this separates the card within the blue one and outside the blue one. So the card outside the green one, not given in the picture, you see, this actually gives the nonlinear periodic waves. So this is the Supersoliton. Oh, actually conditions are just like this. Soliton after the formation of double layer, separatrix that appears to start and end at the origin envelops another separatrix through non-zero saddle, and this separatrix also encloses two saddle fixed points, two non-saddle fixed points. This is the criteria for Supersoliton. This one, clearly you can see. This is simply Soliton after the formation of double layer. You see, this is M is equal to M ppdl plus 0.0017. This gives the Supersoliton. But if you can consider this one, M ppdl plus 0.004, this is actually same as Soliton, not the Supersoliton structure, because you have only one separatrix corresponding to the card P5, and this one gives the right one is the M is equal to M ppdl minus 0.001. This is the Soliton, and you see there is no distinction between these two cards. There is no distinction, there is no qualitative distinction between these two cards. That is the separatrix in the right and separatrix in the left. So, but separatrix in the right, this gives the Soliton before the formation of double layer. But this one gives the Soliton after the formation of double layer. And this gives the transition from double layer to Soliton. You see, we have Soliton, you see that that is the distance between solid circle and the star near at the origin decreases and ultimately collapse at the point after the point xi epsilon is equal to 0.0035. So starting from Soliton, we have double layer, and from double layer to Supersoliton, and Supersoliton to Soliton again. So for Supersoliton, you must have at least two saddle point and at least two separatrix. and the separatrix through the origin must include the one separatrix through a non-zero saddle point. This is here the one saddle you see, 0. In 0 you have a saddle here because you have a solid circle, and for non-zero saddle you have another solid circle, and non-zero saddle, for a non-zero saddle you have another separatrix. You have another separatrix passing through that saddle, non-zero saddle, and you have a separatrix through non-zero zero through the saddle. You have a separatrix through 0. 0 is a phi is equal to 0 is a saddle, and this corresponding to the Soliton structure. Okay, and you see this is actually starting from m is equal to mppdl plus epsilon. After epsilon is equal to 0.0035, the Soliton structure, there is no distinction between Soliton of just before and just after the formation of double layer. This is also same structure. Saddle points, small circles, and equilibrium points other than saddle points or any dynamical system. And there it is. Here it is. You see, this gives you the actually the here phi is plotted against xi, and this figure clearly shows that is a jump type discontinuity. Both the figures shows jump type discontinuity between two solitary structures just before and just after the formation of double layer. And we have a jump type discontinuity between the amplitudes of solitary structures just before and just after the formation of double layer. Okay, thank you. And these are the references. You see.
Thank you, sir. Thank you, sir, for your very informative talk. Now we have some questions. I request Dr. Chitanshu Kumar Das for conducting the interactive sessions with Dr. Anup Bandhyopadhyay. Over to Dr. Chitanshu Kumar Das. Chitanshu, please unmute. Chitanshu, please unmute.
Sorry. Thank you to our honorable guest, Professor Dr. Anup Bandhyopadhyay, for such an informative and enlightened talk on the Soliton. So we may go ahead to the question answer session. So I request all of the listeners, if they have any question, they may present it in their chat box. So I have some personal question to Dr. Bandhyopadhyay, that is there any physical implementation of this Soliton, means solitary wave? Is there any importance to study this solitary wave? We can apply it to any system to improve the performance of the system.
No, actually, you see, any system is non-linear. You can't make it linear.
Okay.
So, first of all, if a system is nonlinear, and if you take the system, conserve the energy, then you can always generate a soliton. Soliton is just like photon. You see, this soliton comes from the analogy of photon. Okay, photon, you
Okay.
can generate photon only for electromagnetic waves. That is, if you have electromagnetic waves, then you can form photon. But this soliton can be generated for both the fields, for longitudinal as well as for the transverse field. So you may consider soliton just like a particle, just like an impulse. And this impulse is everywhere if you consider the system is nonlinear.
Oh.
And
So
through
it
this,
actually
yes.
it actually help us to study the system, nonlinear system more accurately.
No. Any linear system, this gives the idea of the system. And after
Okay.
getting the idea of a system, you can easily develop it from linear to a non-linear, either
Okay.
studying or yes.
Okay. So my next question is that means if anyone want to do research in this field, so where is that scope that he can contribute something in this field?
No. You see, actually, this Soliton, you can go through the Soliton, and Soliton helps us to know the, suppose you know the electric field. What is the electric field of the system? What is the magnetic field of the system? And electric field, magnetic field, etc., etc. This depends on the nonlinearity of the system. And if you
Okay.
take the system is linear, then you can use the simple linear waves and get it the and you have got the magnetic field, that is the intensity of the magnetic field, electric field, etc. Wave mechanics, this helps you to know the structure inside the field. Okay, this is
Okay.
nonsense.
Sir, here is a question from the audience.
Yes.
He asked that which type of plasma components can contain a supersoliton wave, and the second question is the condition to find it in plasma. So first, there are two questions simultaneously. The
Actually,
first
at
question,
least
the first question is which
yes.
type
Actually,
plasma component can contain a
yes.
supersoliton wave?
Yes, at least three component is necessary to get the supersoliton structure. Three components means, actually you see, in plasma we have two components, at least two components. One is electron and the other is ion. And if you have another, say, component, say dust particles or neutral particles, or if you consider two types of electrons, okay, two types of electrons having different distribution in phase, then at least three components is necessary to get supersoliton structures.
Okay, there is another question. How solitons are expressed in fiber optic system?
Yes,
How
pardon me.
solitons are expressed in a fiber optic system?
Actually, fiber optics, you see, the fiber optic solitons, this is actually generated from the KDB like equations or different types of equation. Here we generate solitons from these solitons are simply the steady state solitons. But fiber optics solitons, these are generated from KDV-like equation, and these are the non-steady state. Actually, these are the these KD equations and other equations. These are gives you the soliton with dependence of time. Here we get the soliton with independence, that is the soliton in the steady state soliton. But if you fiber optic system, if you consider the fiber optics, then this gives this gives the soliton where the uh, time plays a very crucial role. Okay, so to study the fiber optic system, it is necessary to 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 describe the soliton through the equations, that is the through KDV and other MKDV or another type of equations. Okay, there are so many equations you can generate the solitons.
Okay, sir. Thank you for your valuable feedback. So I think there is no more important questions I can look here. So thank you for your speech. So we may go for the next session.
Thank you, Dr. Anup Bandyopadhyay, and thank you, Dr. Sitangshu Kumar Das. And now we have our principal sir, Dr. Shyamolendu Chatterjee. Now I request Dr. Shyamolendu Chatterjee to give her some encouraging speech about our webinar.
Am I audible?
Over to Dr. Shyamolendu Chatterjee, Principal of Chittaranjan College.
আমাকে শোনা যাচ্ছে?
হ্যাঁ স্যার।
হ্যালো, শুনতে পাচ্ছ?
হ্যাঁ হ্যাঁ হ্যাঁ।
I am extremely grateful to Dr. Banerjee for his enlightened lecture, though the subject is gripped to me, but I think the subject students and particularly teachers from different colleges and universities are enriched by his scholar's speech, by his scholar discussion on Soliton, and this theoretical mathematics. It is first incident, and it is a remarkable event in our academic sphere of my college. I am grateful to Dr. Jayasree, head of the department, mathematics department. She has arranged this lecture, arranged this webinar. Also Dr. Shitangshu Das, who conducted this program nicely. I think that in near future, mathematics department also arrange more popular lecture on mathematics, and I expect Professor Bandhyopadhyay also will be here to deliver few popular lectures on mathematics, so that we, the bottom line of the subject, can enjoy that. Thank you.
Thank you, sir. Thank you, sir, for your encouraging speech. Now I invite Professor Sanghamita Banerjee for her vote of thanks.
Am I audible?
Yes, you are audible.
Am I audible?
Yes.
Good afternoon, everybody. We thank Dr. Anup Bandhyopadhyay for sharing amazing presentation on Soliton, a quantitative approach. With this, we come to an end of our one-day national webinar organized by Department of Mathematics in collaboration with IQAC, of Chittaranjan College. I'm sure all of you enjoyed today's talk and learned many new things. It may be useful in your future research work. I thank the speaker for spending his time in making insightful presentation and also thank all the participants for their active participation. I'd like to thank our respected principal sir for his encouragement and support to conducting today's webinar. I'd like to thank our colleagues for their constant support to make a successful webinar. Thank you all guests, delegates, resource persons, and all participants for being the part of our national webinar. Thank you.
Thank you, Professor Sanghamita Banerjee. Now, with this talk, we end this webinar here. Feedback link is in your chat box. You can fill that feedback links within today 8 p.m. Um, and feedback link will also be shared in your official WhatsApp group of this webinar, and we will mail in your mail ID also. And please fill the feedback link between 8 within 8 p.m. today, and and please wait for your certificate. We will deliver that certificate within 15 days to your registered email ID. Thank you all participants. Thank you all delegates to this for the to make this webinar successful. Thank you.